Okay, this is the first of a set of two walkthrough videos that I put together to discuss the buffer solution labs. So there are two. In a standard semester, you would have done two buffer solution labs back to back. So one followed by the other. And in each lab, you would prepare a series of 3 buffer solutions. During week 1, you would do this and then titrate it with a strong acid to see how the addition of that acid affects the pH of the buffer solution. And in week 2, you would have instead titrated your buffer solutions with a strong base and observed how that affected the pH of your buffer solutions. So since this is week 1, I'm going to discuss the preparation of a series of buffer solutions and the effect that adding strong acid has on the pH of that series of buffer solutions. I'm going to be using formic acid for my example here with a pKa of 3.74. Generally, when we do this lab, the way that it works is we have a series of acids, and so I assign some groups to work with one and other groups to work with another, and so on and so forth. Remotely, what I do is if your last name runs A through M, you have to work with the acetic acid data set, and if it runs N through Z, you work with propanoic acid instead. So when you go, and I'll put this in the message when I send everything out, but when you go to download the data sets, make sure that you are downloading the correct one depending on whether you're required to work with acetic or propanoic acid, because there will be 2 data sets, so know which one you need. For all acids, the pKa will be given, so you don't have to look it up or calculate it or anything like that. Each data table I prepared will give you the pKa value, so that's one thing you don't have to worry about. As far as preparing the buffer solution, and I'm assuming by this point, judging by the syllabus, everybody has been introduced to the concept of a buffer solution and knows like what it is. And so, you know, what you do, you have a weak acid. And again, my example here is formic acid and its conjugate base, both present in a solution. And the combination of that weak acid and its conjugate, theoretically, allows you to kind of preserve the pH of the solution upon the addition of a small amount of strong acid or strong base. So that's kind of a fancy way of saying that, you know, for a buffer solution, if it's prepared correctly, the pH shouldn't change very much if I add a small amount of acid or base to it. And then that really is where like the title comes from. A buffer solution, it buffers the pH against, you know, any changes that might result from adding a strong acid or a strong base. So I have the mechanism sketched down here for those who wish to see it. Basically, this is my formic acid molecule. The electron pair forming this bond falls back onto the oxygen atom, while the lone pair over here attacks the hydrogen and, you know, forms a water molecule. So again, if you had been in the lab, you would take as a formic acid solution, for instance, and you would titrate it with sodium hydroxide to make the buffer. And that's sheet 1 of the data sheet, because there are going to be 2 sheets. Sheet 1 deals with the initial pH calculations that I'm going to go through. Sheet 2, analysis, deals with how the pH changes once you've prepared the buffer solution and you're titrating it with a strong acid. So sometimes it's easy to get confused. Part 1, you're titrating with a strong base to make the buffer solution. Part 2, you're titrating the buffer solution you made with strong acid. So part 1, strong base. Part 2, strong acid. The strong base is only just, we're using it to make the buffer solution. The strong acid is how we monitor changes in its pH. Calculating the buffers or pH for a buffer solution, it's not a hard thing, but I find that it's often presented in a really unclear and confusing way. So like when I had to start teaching this lab, it had been years since I had done like acid base calculations, and I kind of had to reteach myself, and I was like appalled at how bad a lot of people's lecture notes on this stuff are. It's no wonder I failed the acid-base exam when I took it, when I took chemistry 2. And I did. I failed it. I'm perfectly comfortable admitting that. I did a horrible job on it. It's because it was just presented in such like a disorganized, overwhelming way. So I'm hoping that these notes and the flow chart and everything is going to kind of present it in a way that's friendlier, more user-friendly and more approachable. So we'll see, but that's the intent. To get the pH, you use something called the Henderson-Hasselbalch equation, but you need 3 values to be able to use the Henderson-Hasselbalch equation. You need a pKa, which I'll give to you, so you don't have to worry. This will be different depending on the acid that you work with, but I'll give you that value, so you don't need to worry about calculating it. You need a pKa, you need a conjugate base concentration, and you need a weak acid concentration. The thing to understand about this is that you use up some of the weak acid in solution to make the conjugate base. So the weak acid concentration in your buffer solution is going to be less than when you started, because again, some of this gets used to make this, so this concentration here decreases as you make the buffer solution, and that introduces like an extra step. As far as doing the calculations, I have like a little flow chart here. You're going to calculate the amount of conjugate base, like the molar amount, and you'll calculate the molar amount, the initial molar amount of weak acid, so what you start with, okay? Then you'll consume the molar amount of acid, or you'll calculate the molar amount of weak acid that's consumed. Okay, so the first 3 steps, you're going to get your molar amount of conjugate base that you made up here. Then you're going to calculate the molar amount of weak acid you start with, and then you're going to calculate the molar amount of weak acid that gets used up. So 3 values. Start with, used up. Or, sorry, produced, start with, used up. 3 values. Once you have those, on step 4, you're going to calculate the concentrations. So you'll get your concentration of weak acid and conjugate base here. And once you have the concentration of the weak acid and the conjugate base, you can use the Henderson-Hasselbalch equation to get your pH. Okay. So I wrote the general form of the reaction that we're carrying out up here to prepare our buffer solution. Okay. This is generic. I'm just using HA, B, A, so on and so forth. So these calculations are not specific to the acid that you are using. Okay. So step 1, calculate the amount of conjugate base produced. Okay. And again, we're assuming everything is 1-to-1. That's important. No matter what acid you work with in this lab, it will be a 1-to-1 reaction to produce the buffer, so no need to worry about that. The calculation is just as such. You look at how much base you used in milliliters, because again, what you would have done, you would have taken your weak acid and you would have added strong base to it using a burette. So the burette measures the volume of base that you've used or dispensed. So we're going to start with the volume of base that we dispensed and go to moles of base. And then if you just look at the reaction, right, this is our strong base, this is our conjugate base. The ratio is 1-to-1. For every 1 mole of strong base that's consumed, you produce 1 mole of conjugate base. So milliliters of strong base to moles of strong base, moles of strong base to moles of conjugate base. And that's how you get your moles of conjugate. Now, to get my weak acid molar amount, I need to figure out how much I started with and then figure out how much I used to make A minus here. And that's going to, if I take the difference of those two, that's going to tell me how much weak acid I have in my buffer solution left over. So step 2 is getting the initial, the amount of weak acid I started with, and that's easy. You're just going to take the milliliters of weak acid. You're given the concentration, and I'll show you on the last page how that works out. You're given a table, and it tells you the concentration and it tells you the volume. So all you have to do is just standard, milliliters to moles, and that gives you your initial weak acid. To figure out how much you consumed, it works out to be the same calculation as the conjugate base molar amount, because again everything here is 1-to-1, and you have same amounts to start with and everything. So same thing, milliliters of strong base to moles of strong base, moles of strong base to moles of weak acid. So up here it's moles of conjugate base, down here it's moles of weak acid. So the setup is the same, but they are different calculations. Sometimes people get confused. These are different. This is to get moles of conjugate base, this is to get moles of weak acid, and I put consumed next to that. So you got initial right here, you've got consumed right here. And at this point, right, it makes sense. If you take how much you started with and subtract how much you used, that's going to give you how much is left, and that's going to be the amount present in your buffer solution. So, okay, step 4, calculate your concentrations, right? Because all these are molar amounts here. So for the conjugate, it's easy. I've got moles, and the volume of every solution is going to be 100 milliliters to keep everything consistent. So that's easy. Just take moles of A minus divided by 100 milliliters, or 0.100 liters, and that gives me my concentration of A minus. Okay. To get my concentration of weak acid, it's just what I set up a minute ago. Initial minus consumed divided by volume. That gives you your weak acid concentration. So once I have these two things, I have my pKa up here, I can use the Henderson-Hasselbalch. It's easy. It's basic algebra. Conjugate base goes on top, weak acid goes on the bottom. Take the common log of it, and then just add that to the pKa value, and that gives you your pH for the buffer solution. That's all there is to it. So again, sequence of steps. You need two things here. You need the conjugate and the weak acid concentration. The conjugate concentration is step 1. The weak acid concentration requires 2 steps because you have less in the buffer solution than what you started with. So you take the initial, subtract the amount that's consumed to make A minus. That gives you the amount left over, and you'll just divide everything by 100 milliliters, and that gives you your concentrations, and you can get your pH value. I've got a sample calculation on the second page here. Okay, so this is, the steps are the same as what I did on the previous page. It's just I filled in with actual numbers as opposed to like a generic thing. So you can kind of see how this works. For this particular example, right, if the argument of a common log is 1, then this actually comes out to be 0. So the pH of the first solution is just going to be the pKa of the acid. But obviously, the point of each buffer solution is that you use less and less strong base. So the composition of the buffer solution changes, right? If you use less strong base to make the buffer, you use less of this, so you get less of this. In other words, each successive buffer solution is going to have less conjugate base present, okay? And that's going to affect how the buffer solution preserves pH. And I'll get to that in just a minute to kind of discuss what you should expect to see there. But anyway, this is the table, basically. I kind of sketched. So like this is the table for solution 1. You'll have 3 of these on your first spreadsheet. They'll be labeled like solution 1, solution 2, solution 3. And for each solution, you've got a table like this where it gives you concentration and amounts of weak acid and strong base. So, if you look up here, step 1 to get the concentration of conjugate base, right? Okay. Well, let's look down here at the table. Strong base is my sodium hydroxide, right? And I've got 50 milliliters at 0.25 molar. And that's what goes in up here, 50 milliliters at 0.25 molar. For the acid, okay, well, same thing, right? I've got 50 milliliters of 0.5 molar acid. 50 milliliters of 0.5 molar acid. So you can see how those values are going to come, you know, from the table for steps 1 and 2. That's why the table's there. You've got a water column, and again, what happens is for each successive buffer solution, you use less base. So we add water in increasing amounts to, again, keep the volume consistent. So that way every buffer solution has a volume of 100 milliliters. That's the only purpose that the water column serves. You'll see, like, you know, for the first buffer, or for the second buffer solution, I think water is like 15 milliliters, and then for the third it's 35. That's just to keep volumes consistent. So underneath the concentration volume table for each solution, there's a place where you can record the conjugate base concentration and the weak acid concentration, and then under that there's a box for pH. I even put an asterisk with the Henderson-Hasselbalch equation next to it for every calculation, so you know. So you just can plug this in here, plug this in here, log of that, add the pKa, and that gives you your pH value. And that's the first spreadsheet. You're going to calculate the pH like this for each of your 3 buffer solutions. And again, each successive buffer solution uses less strong base, so there's going to be less conjugate base present in the buffers. Okay. The second sheet, which is titled Analysis, is where you're actually going to make some charts or scatter plots. And what you're basically doing is, if you had been in the lab, you would have taken your buffers after you prepared them and titrated them with hydrochloric acid. And again, using a burette, that tells you how much acid that you've added. And you would use a pH meter to track how the pH of the buffer changes as you add strong acid to it. And so in theory, what you should see happen is, as you use, as I said, like each successive buffer solution, you use less strong base. That means that there's less conjugate base present in your buffer. Okay, so the ratio here of conjugate base to weak acid for each successive solution, this is less and this is greater because you're making less conjugate. So what that means is this ratio of A minus to HA for each buffer solution is less than the previous solution. And what you should see is, as this ratio decreases, it should take less strong acid to affect the buffer's pH. So like the first buffer solution, it may take like 20 milliliters. And then the second buffer solution, where there's not as much conjugate present, it may only take like 14. And then the third may only take like 10 or something like that. In general, as that ratio of A minus to HA decreases, you should see that it requires less to start dropping the pH. The pH is going to drop more rapidly. It's going to require less acid to do that. Formally, what you're going to do is you're going to figure out how much acid is required for each buffer to drop the pH by 1 unit. Okay, so my starting pH here is 3.74. So the question is, for each buffer solution, how much does it take to drop the pH? Like, so for instance, like I said, my first buffer solution, my starting pH is 3.74 because, again, it's just the pKa value, right? If we go back here, what I calculated for my first buffer solution is just the pKa because the log term zeroes out. So the question is, how much acid do I have to add to my first buffer solution, for instance, to drop the pH to 2.74? One thing that I had experimented with when I taught this lab back in the spring, and the shutdown had just started and everything was chaos, and I was just trying to get this stuff done as quick as possible for everybody. One thing I tried to do was do a straight line fit like we've done 1,000 times, and then actually calculate using that line, what X value do you get 2.74. That failed miserably. You get a really good straight line fit if you do this. You get like 0.95 for your R-squared value. But if you look, like the y-intercept should be your starting pH, right? Your starting pH should be like 3. So you would expect the y-intercept, if I did the line for this graph, the y-intercept should be about 3.74. That's not what happens when I do a straight line fit. Even though it's got a really good correlation, value. The y-intercept is like 3.93. It's really far off. And so what I found when I actually took the equation of the line, it doesn't work very well. You end up getting results that are, you're getting like 40 and 55% error values. So do not do straight line fits. It seems logical, but I think the problem is that as you go further and further out, when the pH starts to drop measurably like this, you don't really have a buffer solution anymore. The whole point of a buffer is to prevent large pH shifts. So as you go down this curve and you see the pH drop more and more steadily, you're not really working with a buffer anymore at that point. And so I think these points out here kind of throw the slope of the straight line off, and it just makes estimating really inaccurate. So instead, all you're going to do is you're just going to look. So my pH was 3.74. You have a table for each buffer solution of acid volumes next to pH values. Okay. If my starting pH is 3.74, I'm looking, a 1 unit drop is 2.74. What I'm going to do is go to my table and find the values closest to 2.74. Your value is probably not going to show up on the table. Mine doesn't. The two closest I had, 2.74 falls between 2.90 and 2.68. So these are the values I have to work with. This falls between these two, so I'm going to use these two values. Okay. All you're going to do is take the volumes associated with those two pHs and just average them. So I took 18 and 23, averaged them. That gives me 20.50 milliliters. So I'm going to say for this example, it takes about 20.50 milliliters of acid to drop the pH by 1 unit. That's what my X here should be, roughly. Would be like about 20.50 to incur a pH drop of 1 unit. And you'll, like I said, you'll do that for all three of your buffer solutions. Again, just be aware, part one, you're calculating these starting pHs. So for each buffer solution, your starting pH is going to be different. That's what part one is all about, is getting the starting pH. You'll use the Henderson-Hasselbalch to do that. And then just look at your graph and your table and say, okay, what two values are closest to that 1 unit drop, and just average the volumes associated with those. And report that as the amount of acid that is required to drop the pH by 1 unit. Like I said, as you go from buffer solution 1 to 2 to 3, you should see that it takes less acid. So like if this takes about 20 and a half, maybe the second one takes 17 and the third one takes 11 or something like that. You should see, as this conjugate base to weak acid ratio gets smaller, you should see the amount of acid required drop quite a bit. And that's just because there's not enough, there's less conjugate present in the buffer to neutralize that acid that you're adding. So it's going to get, consumed more quickly and start to cause the pH to drop more rapidly, faster. So, and that's the lab. I mean, really, the first part, you're just going to calculate your initial pH for each buffer solution. The second part, you're just trying to figure out via estimation how much acid does it take to drop the pH by 1 unit. And you should see, again, the smaller that A- to HA ratio, the less acid that it takes. So next week we're going to do, the calculations are very similar, but you're going to be titrating with a strong base instead. So you'll take like a weak base, titrate it with a strong acid to make your buffer, kind of like the reverse of what we did here, and then titrate it with a strong base to see how its pH shifts. So that's going to be what we do next week. It's similar. You'll get some of the same numbers, so don't freak out if you're like, you're not going to get the same pH values, but it's just a lot of these numbers that you do on week 2 are going to be like numbers that you're like, I think I saw that when I was doing calculations for week 1. That's not indicative that you made a mistake. If anything, you're probably doing it right. So that should be about it for this one.